welcome to joint quantum colloquium. So as some of you guys know, we have actually quite exciting program today, but also in the next few weeks. So in particular, next Wednesday, Professor Sholkov from Yale will talk about superconducting qubits here at this time. But today it gives me a great pleasure to introduce Professor Gerhard Rempe from Max Planck Institute for Quantum Optics in Munich. Gerhard completed his PhD and his habilitation in Munich at the end of 1980s. At the time he was working in a group of Herbert Walter, and in this work he developed and explored, realized experimentally and explored a maser which was quite unique at the time. So it basically worked by just using one atom at a time coupled to the high Q microwave cavity, and basically in this system Gerhard was able to control the properties, quantum properties of the photons, microwave photons emitted and stored in this microwave cavity in quite kind of unique and remarkable way. So that work truly jump-started the field which is by now known as cavity quantum electrodynamics. In the past 3 decades, this field expanded quite dramatically. In many ways it kind of gave rise to the field of experimental quantum information science. So over this time Gerhard remained both a pioneer and a world leader in this exciting field, and he has made a number of kind of groundbreaking contribution to this field. So between 1990 and 92, Gerhard was a postdoctoral fellow in a group of Jeff Kimball at Caltech, where he started experimenting with Qubit-qubit systems in the optical domain, and then he moved to start a new research group at the University of Constance. Before in 1999 he was called back to Munich to become a director of Max Planck Institute. Gerhard's contribution in the field of cavity quantum electrodynamics involve a wide range of experiments which are basically exploring quantum interface between light and matter, and eventually these kind of techniques which gave rise to the concepts of such as quantum networks and quantum internet, and some of that will be a subject of today's talk. But this is only part of Gerhard's activity. So in addition to his work on Qubit-qubit, Gerhard also has done kind of numerous groundbreaking experiments in the fields of atom optics and quantum gases. So his experiments that he's carried out in Constance on wave-particle duality are by now part of quantum mechanics textbooks. He was also has a distinction of creating a first Bose-Einstein condensate outside of the United States, and and with this ultra-cold atom systems he has done many wonderful things, including, for example, realization of strongly correlated atomic systems using the counterintuitive concept of the quantum Zeno effect. Last but not least, I would like to mention Gerhard's pioneering work in the field of ultra-cold molecules, where he developed quite unique and kind of remarkable approach for cooling and manipulation of ultra-cold molecules, and he is now using this kind of systems for a wide range of applications, from ultra-cold chemistry to quantum information. With that, I'd like to welcome Gerhard to the joint quantum colloquium, and I'm looking forward to learning whether the quantum internet is a vision or fiction.
Yes, thank you, Misha, for this. Is it on? Yeah. No? Information pleasure for this long and detailed introduction. The thing is, if you get older, there's more and more to report, basically. So thank you very much for this kind of invitation. I'm really happy to be here. This is a place where all these wonderful experiments happen that bring the world of quantum optics, quantum information forward. It's really great. So I'm spending here 3 days or so. This is the first day. I'm already totally exhausted, basically. I have to give a talk now. Anyway, good. So, having said that, this is a little bit of political statement here, because it shows Europe. No? And the US is somehow connected here with this little photon. But it comes from the fact that we have this flagship program. The European Union started a $1 billion, or €1 billion, I should say, flagship program in quantum information science. And we have just started, so to say, to collaborate on a project where we would like to build such kind of quantum internet between European cities. I'm not sure how fast that will proceed, because I will tell you about, so to say, all the issues that one needs to cover. But I think we have a wonderful consortium, basically, and yeah, we have a great time. We're fun of doing this. So I will tell you a little bit of what the status is in my lab. But let me sort of say, first point out, I prepared this talk a little bit for the broader audience, so I will not go into any of the details. You should ask questions, and you can also ask questions during the talk if you want. But I will really sort of say, like to say what are some of the underlying principles and so to say the new tools that we have available at the moment. Yeah. So let me start with a little bit historical introduction. So this goes back to the mid-1990s. Rolf Landauer asked the question, is quantum mechanics useful? Of course, quantum mechanics is useful. We can calculate the energy levels of the hydrogen atom and all these nice things. But I think he was really asking, is it useful for society? Can one earn money with it? Except becoming a professor, maybe, in quantum physics. And his statement was kind of very critical. So he outlined in this paper, and there are more papers, there's a series of papers actually, he was kind of skeptical. This paper is a warning signal. This possibility is beset by problems. And what he means by this possibility is that to build a quantum computer. Okay? And he brought forward many reasons in this paper and also in the other papers. He brought forward many reasons, 1,001 reasons to some extent. Well, he didn't mention 1,001, but he brought 10 or 20. And he really discussed it. And this is all for him reasons against quantum computation. He did not say this is not possible, but he wanted to bring forward some of the things that one has to consider. And this is a small list of what basically he said. There are too many qubits one needs. There's too little control over these qubits. There are too many errors one is making. And in the end, and this is a very important point for him, for Landauer, too high costs. How can you compete with this quantum computing environment, basically? How can you compete in terms of cost with a laptop or with a smaller computer? And he basically asked them the question, given this fact, and of course there's lots of progress since '95, but still some of the issues that he raised are still kind of valid. He really asked the question, is it desirable to set up a research program towards quantum computation? This was '95. There's another paper which is just the opposite. This is a paper from Jonathan Dowling and Gerhard Milburn in 2003 or so. And I think, to the best of my knowledge, maybe they coined this term, the second quantum revolution. They were very optimistic about it. And they basically wrote here, the first quantum revolution gave us new rules that govern physical reality. This is basically calculating the energy levels of a hydrogen atom and things like this. And then they continue and say the second quantum revolution will take these rules and use them to develop new technologies. And of course, this is a very optimistic statement, and we're all excited about it. So in some sense, this field of quantum information science or quantum computing, quantum networking, quantum algorithm, quantum computing, quantum simulation, quantum chemistry, and so on, quantum machine learning, this has split up in a large number of different disciplines, basically chemistry, physics, mathematics, computing, biology, and so on. Many of these things that are behind this are ideas. Most of it, I would actually say, are ideas. There's not so much actually implemented in the lab, which would be useful in the sense that Landauer was asking for. There's one thing which is genuine quantum, and this you can buy, there are companies and so on, and this is definitely useful, I would say, and this is in quantum communication. It's basically a scheme to communicate between two particles, or two objects, Alice and Bob typically. They communicate, and they of course want to keep it in a secret way, and they encrypt their messages therefore, and this encryption is based on a purely quantum mechanical theorem named the no cloning theorem. You cannot clone a qubit, you can clone a sheep, you can clone whatever, many things, but it's very difficult to clone, or it's impossible to clone qubits. Well, you can do something around it, post-selected and so on, but typically there's no cloning. You cannot copy a quantum state. And this is basically the underlying principle, which is genuinely quantum. So quantum communication is something which really works. And why does it work, and what benefits does it have, for example, in terms of quantum computing? So I could bring up, let's say, 1001 reasons for quantum communication. Well, first of all, it's useful because it's secure. It allows for secure communication. It has, in principle, only a few qubits. You're sending single qubits, one at a time, basically. One qubit after the other, which is much easier than building a quantum computing machine which consists of many qubits, as Landauer was pointing out. So only a few qubits, which is an advantage because we don't need that much of a control capability. That's one thing. But the challenge is, of course, that these qubits are of different kinds. There are flying qubits, there are stationary qubits, material qubits, light qubits, and this is what makes it really a challenge to bring these different kinds of qubits together. And this is one of the big problems, so to say, big challenges, big things to deal with, that these different kind of qubits effectively talk to each other. And to some extent, it's beyond imagination. I'm coming back to this, beyond imagination, because this quantum communication over some distance is what does not exist in nature. So in the end, it's not so clear what kind of effects or what kind of things we will see once this is all implemented. One has these huge quantum systems, which maybe at some point are spanning the whole world, or the whole Earth at least. So there's lots of things to think about this. So quantum communication definitely is useful, and I would say it's desirable. And this is why people are really investing a lot of money into this. Billions of dollars is invested by the Chinese government into quantum communication with satellites. They have this quantum satellite here, which basically connects or can connect two very remote locations, like one in China here, and the other one is in Austria. So if you look into this in more detail, the question is, what is actually quantum about this? The sender here and the receiver there, or vice versa, the receiver here and the sender there are of course both classical objects. These are Alice and Bob, these are people like you and me. So it's truly classical. There's nothing quantum. There's absolutely nothing quantum in that system. They're not establishing a quantum system which is as large as something that goes from Graz here in this case to this Chinese city. They're using the quantum effects that I mentioned before, this no cloning theorem. They're using this quantum effect to distribute a key. So basically it's quantum key distribution between classical observers. Classical observer here, classical observer there, nothing quantum. Only the link. The link is established in a secure way by means of quantum physics. But otherwise this is a pretty classical thing, I would say. So we would like to go one step further with this quantum internet idea, because the idea is to have quantum states distributed between quantum memories. So it's no longer Alice and Bob as a classical observer or classical sender. It's really a quantum system which can store quantum state, which can produce quantum states, which can progress quantum states. And these quantum states are then distributed between different locations. So this is a quantum computer, for example. As you can see here, it's spin pointing up and down at the same time. It's like a quantum computer. And this quantum computer, for example, talks to another quantum computer somewhere else, at a remote location. Okay? And this, in the end, requires, if you like, this is one of the dreams, if you like, to have something like a quantum cloud, a global quantum cloud, like we have a classical cloud at the moment, where we store classical states, which we use for distributed computing, for example, in the classical way. We are thinking about similar things in the quantum domain. So we are thinking about a full quantum architecture at some point, it's not in the distant future, let's say. We are thinking about a full quantum architecture for some global quantum cloud available. So to some extent, this quantum internet is both more visionary than a quantum computer, let's say, because we would like to connect different quantum computers. In order to connect them, we would need quantum computers. So in some sense, the quantum internet is beyond quantum computation. On the other hand, it's also more realistic, because maybe in the end we don't need as many qubits that we want to transmit. So there are different aspects of the scenario, and these different aspects really make it interesting, because we can proceed step by step, basically, into this quantum internet idea. Start with a few qubits, which is maybe realistic, and at some point have this vision of connecting quantum computers. And the big problem basically is this. There's a quantum computer, which I'm sure will be built in Harvard very soon, Misha. There's this cable here, which we have. And the question is, how do you connect this cable with a quantum computer? So what's the interface? What's the interface? How do you connect two quantum computers? You cannot do a measurement and then transport the result of the measurement somewhere. We need this connection somehow. And this is one of the big problems, or one of the big challenges. So let me just briefly say why is this a problem. So there's a memory here, and it stores a quantum state. So it's a superposition, let's say, of ground and excited state of something, an atom, for example. The question is, you want to bring it from here to there. So how do you do this? Well, the easiest thing is put it on a truck, put the lab on the truck, drives the truck somewhere else, and continue with the experiment over there. So this can be done, I mean, in principle at least. I'm not sure if you really want to pack a full optical table onto a truck, but in principle it's possible. Okay, you need electricity, but batteries and so on. So this is all doable. And I'm not sure, at the end, you can transport many qubits on a truck. You can also put many hard drives, classical hard drives on a truck, and transfer information via just moving it. But somehow it's not very elegant, and it's expensive, and it's not so scalable, because then the trucks would drive around everywhere with all these big lab spaces on top. I'm not sure if you really want this. So the more elegant solution is probably take this qubit and map it onto a photon. For example, the excited state can emit a photon, then goes into 1, and the ground state cannot emit, and it's a 0. So in some sense, the 0 plus 1 is a superposition state which resembles the original qubit. It's not a very good superposition state, because photons can get lost very quickly, very easily, and then the 1 turns into a 0 and the quantum state is lost. So this is a very bad qubit in my view. So in the end, we will use polarization qubits, which are better. But for the purpose of the argument, this is fine. And then we send this photon somewhere else, and we read it into a memory. The question is, how do we make sure that this local memory with the state E plus G, with this state emits a photon in the direction I want? Okay, Misha, I want you to have the photon. So how do I do it? And in the end, you get the photon, but I don't want it. I want to send it to him. So the question is, how do you do it? And this is done in 2D. We build an optical cavity around the qubit. So here's my qubit with the excited and ground state, and we build a cavity around it. And the magic thing is that we can achieve a regime which is the strong light matter coupling regime. It's basically described by Hamiltonian like this. You take the energy of the atom or the molecule or whatever it is and put it into a photon. And this can be done with some coupling strength G, and this coupling strength G can be made really very large if you go to cavities which are really small. So in that sense, my atom would be my quantum memory, and my cavity would be my quantum interface that sends photons into a certain direction because they can escape through this mirror, which has some reflectivity. Okay, so this is one of the cavity systems that we have built very recently. It's actually a two-mode cavity QED system. It's two optical cavities. There's an optical fiber here, there's an optical fiber there, there's one from top, one from bottom, and this is a mode. This is a mode of one cavity, this is a mode of the other cavity, and then there's a single atom here. Okay, the single atom is called, which is a memory in the end. When I show you this picture, because it's most recent, it's basically just coming out of the lab, we have finesse of these fiber resonators of up to 200,000 or so, but it's not yet functional. It's not yet functional in the sense that I do not show you results of this particular system. Okay. So this is our atom. We trap the atom. We can keep it there in this crossing point of the two cavities or in the optical mode. It's a challenge. I should say it's really a challenge to keep the atom there. It took us something like 10 years or so to bring the atom there, to cool it, and to do experiment with it. And one of the reasons why it's a challenge is that in contrast to free space experiments, optical access is very confined. There are mirrors all over the place. So it's very difficult to bring in laser beams from all directions to laser cool, for example, the system. It's impossible because in different directions there are optical cavities. And so this is one of the reasons. Another reason is there's this Purcell enhancement. Purcell enhancement meaning that a cavity, which is an atom which is excited, emits preferentially into one of the modes at a faster rate than in free space. So this is good news. The bad news is that all the light forces also increase with the Purcell effect, and also the heating rates, momentum diffusion, and so on, scales also with the Purcell effect. And this is kind of bad news. But in the end, by applying different cooling techniques like cavity cooling, feedback cooling, Raman cooling, I call this lattice cooling, and I don't want to go into the details, you can ask me if you want. In the end, what we achieve, well, we can trap an atom. It works in the end. We have a stationary qubit, it's fully controlled, the internal degrees of freedom are controlled, the external degrees of freedom are controlled, we can control the atom into the ground state of motion in an optical dipole trap, in an optical lattice, and also the optical properties are controlled because we have these cavities very close by, and we control the radiation effects. So let me show you a first experiment that we did with this. A first experiment that shows how non-linear basically a single atom is. A single atom is the most non-linear, optical non-linear device that you can think of. The reason is very simple. If you have an atom in the ground state, it's an absorber. If you send one photon on the atom, it goes to the excited state, it's an emitter. So you're changing the optical properties of the total medium completely, but just shining in one photon. The problem is, or the only challenge is, how do you bring into interaction very efficiently a single atom and a single photon? And this is what cavity QED can achieve. So let me show you the effect of this nonlinear optics. Well, if you take two photons, for example, and you would like to have two photons interfering, typically it doesn't happen because Maxwell's equations are linear. But if you crank up the intensities, you get an effect which basically produces, for example, electron-positron pairs during the interaction, and they can scatter photons. So there isn't photon-photon interaction, but it occurs at very high intensities, like 10 to 29 watt per square centimeter. Nobody in the world has such an intense laser. So this effect has not yet been seen, because basically you need electric fields of 10 to 16 volt per centimeter or so. But in a cavity QED scenario, you can have two photons coming in with one atom as a nonlinear medium, and then power levels, as it turns out, goes down by many, many orders of magnitude to something like 10 volt per centimeter. This is what we have in our lab, or maybe nanowatt per square centimeter intensities coming in. Completely realistic. I mean, nanowatts. This is really easy to do. So how do we do this? Well, there's a cavity here with one atom. Let's say it has two energy levels, ground and excited state. It's coupled by some coupling constant here. And then if you calculate the energy levels of this combined and cavity system, basically it comes in a series of doublets. So this is one quantum of excitation in the system, this is two quanta of excitation, but it comes in a doublet here. It comes in a doublet because atom and cavity couple. The splitting here is G, the splitting is square root of 2 times G, because basically the coupling goes like the electric field, and the electric field goes like the square root of the photon number, and the photon number is 2 here, and that's why we have the square root of 2 there. So we have a nonlinear system. We can derive a transition from the ground state to the first excited state, let's say this one, but that is blocked. It's blocked, there's a detuning here, because of this nonlinearity, because of the square root of 2. So this is what one could call a photon self-blockade. Self-blockade in the sense that if I send 2 photons, one can go in, but the other not, the next one not. So the photons come from the same beam. But we want to have 2 different photons, so we have a more complex and more sophisticated structure. First of all, the cavity supports 2 modes. It could be the cross-dipole trap that I showed before, but in this experiment it was just one cavity with 2 different longitudinal modes, and one mode is resonant from this transition here, and the other mode is resonant on this transition, and they're coupled by some classical beam. The classical beam comes from the side. So now if you plot the energy levels of that system, it basically looks like this. So there's number of energy quanta in one mode, 0, 1, 2, and so on, and 0, 1, and 2, and so on the other axis. So the energy levels is now more complicated. You can see there are no longer these doublets here, but there's a triplet. Well, why is it a triplet? Well, this is EIT. This is a mode 1. It's this transition here. Okay, so this is a lambda configuration. The lambda configuration is known to exhibit the phenomenon of EIT, electromagnetically induced transparency, where coherent superposition of these 2 build up and the system becomes dark. It cannot absorb anymore. If it's dark, it's no longer coupled, so there's a new state right in the middle here. Okay, so that's this one. If I consider the other axis, the G2, which is here, basically what happens is, if I switch off the G1 field, I'm just optically pumping the system from state 2 via state 3 to state 1, and I just have a 2-level configuration, which is empty. Which is empty because the atom is in 1, so it's not coupled. So I'm just going this way. Okay? So going up now is easy because it's EIT, it's transparent. Going sideways is also easy because it's transparent if the G1 is missing. But going diagonal is difficult because there's no state. There's no state here. There are states which are off-resonant, but there's no state here. So now depending on the detuning and so on, I cannot go here. I can go this way, I can go that way, but I cannot go this way. So one photon blocks the other one. Photons of one beam are fully transmitted, no absorption, nothing whatsoever. If I go sideways, nothing happens. Only if 2 beams are present, 2 photons of the different colors, one color here, the other color there, then there's no state up here, and I have total blockade, photon cross blockade. If I detune, well, there's also the probability to have tunneling. So this shows experimental data, for example. The blue one is the empty cavity. The yellow one here is cavity EIT. That's on one line. Shows EIT resonance. There's a normal mode splitting, which is this one and that one. And then there's a very narrow EIT. It has 90% or even higher, 90% transmission compared to the empty cavity. So it's almost fully transmitting. And if I'm just looking at the cavity QED scenario, I just see a normal mode here, and I see a normal mode there, and very, very small transmission. It goes down. So now let's look at the self-correlation of these 2 beams. Well, this is the probe beam and the signal beam. And as I said before, I'm going either this way or I'm going this way. This is EIT, fully transparent. This is an empty cavity, fully transparent. The correlation function is totally trivial. It's 1, it's independent photons, it's laser photons. So there's nothing whatsoever happening in this scenario. But I'm looking at the cross correlation. What does one photon to the other photon? I see this blockade mechanism. So it goes down to 20%. So they effectively, very, very effectively block with each other. The system is asymmetric because we're talking about a cross-correlation. It's not an autocorrelation, it's a cross-correlation. The system has a very long lifetime, like microseconds here, which is much, much longer than what we typically expect from a cavity QED system. Also in this configuration. And this is just the EIT lifetime. This is the EIT state, so to say, lives very long. So I see the EIT lifetime here, and I see the empty cavity, basically lifetime on that state. Okay, so it's a highly nonlinear system. So this is good news, basically. We know that now we can have single photons talking to each other. We can have single photons talking to the cavity. And now what to do with this? And I was advertising quantum communication. So one of the big challenges in quantum communication is, of course, to transfer this quantum state from one place to the other. Ideally, or ultimately, what we would like to have is we would like to send this quantum state, let's say, once around the Earth, or to the opposite side of the Earth. So how do you do this? Well, you cannot send the photon directly. You cannot send it directly because it's absorbed in the optical fiber or diffracted in free space. So you need some other technique. And the other technique, the best technique, which is known at the moment, would be teleportation. Teleportation of the state from one place to the other. But that teleportation needs long-lived memories. Why is that? Well, let me consider this example. This is where I come from. So let's say I want to take a state, a qubit state from here, and bring it to the other side of the Earth, which would be New Zealand from the point of view of Munich here. From Boston, what would be opposite of Boston? I don't know exactly. Anyway, so you want to bring the state to the other side of the Earth. So the teleportation would work like this. You set up entanglement between here and there. This entanglement is then a resource for the teleportation protocol, which requires a local measurement here, communication of the results via classical transmittance channel, communication of this result to the other side, and a suitable rotation down here. This is a teleportation protocol. I don't want to go very much into the details. But this teleportation protocol has as a bottleneck the classical transmission time. So the classical signal has to be communicated from here to there, and that takes 66 or so milliseconds to go half around the Earth, 20,000 kilometers in an optical fiber or so, or maybe free space. It's 66 milliseconds, so it's a transmission time. So we need memories. We need memories which can store single photonic qubits for at least, let's say, 66 milliseconds. This is kind of the benchmark. Okay. These memories don't exist, or at least didn't exist until recently. Here's our memory. So the memory is pretty easy. We take an atom in the cavity, there's this photon coming, it's a qubit, it's a polarization qubit, left and right polarization. We absorb it in the atom. The atom is maybe prepared in that state here. We go into minus and plus one due to angular momentum conservation. We can go into these states. And effectively, if this is a superposition state of left and right, then we will end up with a superposition state there. And we need the cavity to have this directionality. One thing. The other thing is we need this strong light-matter coupling. So we need the cavity. The problem now is, if this is an absorber, and light is coming in, well, it's approaching, this light would not go into the cavity. Okay? There's an absorber in the cavity. There's an absorber in the cavity. You cannot bring light into the cavity because it's an absorber. So the photon will be reflected. It will not be absorbed, it will be reflected. If you have a cavity, you put your hand in, you bring in some light, it's reflected. If you take your hand out, it goes in. But absorber, so it doesn't go in. You see the point? So if the photon is coming here, it cannot, there's an absorber, but it cannot be absorbed because it doesn't go in. In order to go in, it has to build up. It has to build up between the mirrors and destructively interfere in reflection. But it cannot build up if there's an absorber here. So it cannot destructively interfere in backward reflection. So this will never work. You cannot just send a qubit, a photonic qubit, onto an atom in the cavity and hope that it's absorbed. No chance. So what is needed is EIT. So it makes the system transparent. And we know that EIT works. I've shown you data before. EIT works. So basically we need a lambda level scheme here, or in fact for the qubit we need two lambda level schemes going up and coming back down to -1, magnetic quantum number -1 and magnetic quantum number +1. Okay? So the right process requires EIT because now this system is not absorbing. So the photon goes in. It's fantastic, it goes in because it's not absorbing. But if it's not absorbing, it's not stored. It just goes through. That's also not what we want. So the idea is when the photon comes, it's basically a pulse of light. We slow down this light by ramping down the control field which comes here from the side. We slow down the photon and ramping this one down. So basically the light pulse is going in, and when it's coming in, we are ramping this down and arithmetically transfer the photon, which is in this superposition state, into an atomic superposition state. So this is cavity EIT, if you like. And then the reverse process is just doing the opposite. It's called vacuum-stimulated Raman adiabatic passage. You can just turn on this laser again, which drives the system out of these states back into the original state, and the photon comes back out. So this is fully reversible. Then it's fully reversible. You can see here, for example, we made a photonic, can be called a photonic mode converter. We convert photons which are 500 nanoseconds long into photons which are 500 microseconds long. I mean, just the wave packet. By storing the long photon in the memory in a slow process and then reading it out in a fast process, you go from 500 microseconds to half a microsecond, or doing the reverse, you can go from 0.5 microseconds to a long photon, 500 microseconds. And this can be done with a total efficiency, read efficiency of about 20% or so. This sounds all very easy, but in practice it's kind of very complicated. It requires some chirp compensation techniques, which you can ask me if you want, but this goes too much into the details. So how does it work then? Well, this plots efficiency for the storage time, and this is the efficiency, 20%, as I said before, and this is a qubit. Any polarization basically, it decays from fidelity 1 or close to 1 to something like 50% here. The classical limit or the quantum limit, depending on the perspective you have, is 2/3. 66%, so that means the storage time is something like 500 microseconds. We were kind of disappointed because we were shooting for 66 milliseconds. 500 microseconds is way too short. And the reason is that we are using states which are magnetic field sensitive. So it's superposition of this state and that state that we were using, and this responds to magnetic field fluctuations, for example, both from real magnetic field and also virtual magnetic fields induced by the dipole trap with a not perfectly controlled polarization, for example. Anyway, so we make the idea is now to make a Raman transfer from that state into this one, because this one shows the same magnetic field dependence as this one. At least the magnetic sensitivity is much less, 500 times less. So we're making a Raman transfer into these pseudo-clock states. It's not perfect, but into pseudo-clock state, and then we can have lifetimes of something like 10 milliseconds, which is already 20 times longer than what we had before. 10 milliseconds. It's still not enough. Please remember, we wanted to beat 66 milliseconds. So the residual limitation comes from some inhomogeneous dephasing from the atom being in different trapping sites. It could be one atom which hops from one trapping site to the other. These are things that we see in the experiment. But it could also be that from shot to shot, we trap the atom at different trapping sites of the optical lattice that we are using. And this leads to a small inhomogeneous distribution of Stark shifts. And that makes an inhomogeneous distribution of qubit rotation frequencies. But this can be compensated with a spin echo. Okay, so the idea is to replace the qubit with a spin echo by making a pi pulse here. So we're storing the state originally in a superposition of this state and that state. Then we bring this down to this state, then we make a pi pulse into this state, and then we bring this back up and read it out. So it's a complicated set of protocols, which in the end leads to a decrease of the fidelity of maybe 80 or 90% here. But now we have lifetimes on the order of 100 milliseconds or maybe even more. Now we are 200 times longer, and most importantly, we are more than 66 milliseconds. So in some sense, the claim is that we beat the benchmarks that one needs for global teleportation. And so this basically allowed us to set up the first network experiment with two systems. So we have two of these cavity QD systems, one here and one there. They have two different labs separated by 20 meters. They're connected with an optical fiber, which is 60 meters long. And photons can be produced here, or the state of that atom can be mapped onto a photon. And the photon travels to the other system and is now stored in that system, or the other way around. And this allowed us to do some experiments with photon emission and absorption, like state transfer. So the state of the atom here is mapped onto the photon, as I said, travels to the other side, is stored here, or the atom is entangled with the photon, and the photon travels to the other side, is read into that state, into that atom. So we have atom entanglement, and we even made a teleportation experiment. So we teleported the state from that atom into that state. So we basically did this experiment that I was advertising before, this global teleportation experiment we did, but not global, but 20 meters, or 60 meters of fiber. So it's cheating a little bit, huh? But at least the essential ingredients are there somehow. The essential ingredients are there. The problem now is, how do we scale this up to global distances? This doesn't have the technology to do this, or the capability to do this, because the photon just gets lost in the optical fiber. The propagation length is finite. And so this is a big issue. So in the end, what one needs is what's called a quantum repeater. It's basically an entanglement swapping scheme. Basically, you are chopping your long distance into small pieces, quantum memory here, quantum memory there, and you connect these two with faithful interfaces that we have. And the idea is to entangle these two, but we need heralded entanglement. We need to know whether entanglement is established or not, because if we know it for this part, and if we know it for that part, we can make what is called a Bell state measurement here. A Bell state measurement here, and then entangle this one with that one, and then continue on a global scale, and at some point have two memories entangled which are separated by some very long distance. But in order to do this, we need a full toolbox, basically. I call hybrid quantum logic toolbox to achieve this. And let me show you this toolbox. So this is now a different scheme. It's a different scheme which allows much more than what I told you before. Basically, it's based on a technique which allows us to detect single photons in a quantum non-demolition way, a non-destructive detection of a photon. A photon which is propagating outside the cavity, and we have the capability to see whether there is a photon or whether there is not a photon, or what polarization it has or not. That produces, in some sense, and I will explain that to you, that produces a success herald, and it also gives a modular design of these networks, optical cavity with an atom, and photons basically bouncing from the system. So how does it work? Well, it's based on a scheme with Raman and co-workers came up with some 15 years or so ago. If you just take an empty cavity and you take a light field and you reflect it from that, just classical optics gives you a pi phase shift of the reflected field. It's classical electrodynamics, nothing quantum. It's classical electrodynamics. It comes back with a pi phase shift in this scenario. Basically, the photon is reflected from the back mirror. It goes in, comes back out, but with a pi phase shift. If I put an atom there, let's say it's in the ground state, and the cavity is coupled from this, what I call the excited state, to some even higher excited state, it could still go in because the atom is detuned. It could still go in and still comes back with a pi phase shift, but if it's in the excited state, there's this normal mode splitting, it's an absorber, no photon goes in, photon is reflected but now with a zero phase shift. This is a very robust scheme, very robust method in the end to find out whether a photon has been reflected. In the following way, we start in the superposition of E and G, and one photon is coming. It's reflected. In both cases, it's reflected. So the one photon stays in one photon. But the state of the atom, E plus G, changes to E minus G because of this pi phase shift. This state is totally orthogonal to that state, and because it's orthogonal, it can be distinguished. So by making a measurement on the atom, you can distinguish whether there was a photon or not a photon. So in some sense, it works like this. So this is a Bloch representation of the Bloch sphere of the atom, excited state up, ground state low. You make a pi over 2 pi's, rotate the Bloch state in the equator. Then comes the photon, it makes a pi phase shift, which means the Bloch vector goes along the equator. And another pi over 2 pi's brings it into the excited state, and then we look for fluorescence. And that signals are the presence of the photon. If there was no photon, nothing happens here. The second pi over 2 pi's brings it to the ground state. And then there's no fluorescence because the ground state doesn't fluoresce, because the laser derives some transition from the excited state. So that's how it looks like. We send a photon, it's reflected. Where does it go? We send it to the moon. No, we don't send it to the moon. We send it to a detector to make correlation measurement. So here's the detector. But now we look at the atom and see whether the atom fluoresces. And yes, the atom fluoresces. So this is, if you like, a second detection of this photon. But we would not have needed to detect this photon. It could fly to the moon, and we would just see this fluorescence here. And this fluorescence signals us that there's a photon. Okay? If we do not send a photon, it looks like this. Nothing is there, and no fluorescence. Okay? So in summary, you can estimate some numbers, and here are the numbers. Let's assume we have a photon given. We send it onto the system. We see it with a probability of 87%, and it survives with a probability of about 66%. There are losses in the system. There are losses in the system which doesn't make it ideal. These are purely technical losses, but they are there. So in this experiment, it was 66%. But we see the photon with 87% probability. So it's quite a good photon detector, I would say. This is not a qubit. The atom was a qubit. We can make now the photon a qubit, and then we can make gates. So basically the idea is these are the two states that we had so far, excited and ground state, and now comes right and left polarization photons, and only one of them couples to an excited state. So this is the excited state energy level diagram. I don't want to go into the details, but that's how it looks like. And only this state here, this transition here, couples to the photon. Only if the atom is in E and there's a right polarized photon. And then it couples and it's reflected from the input mirror, and therefore there's no phase shift. In all other three cases, there's a minus phase shift. And this is basically the quantum logic of a gate. So let me show you how this gate works. So we're sending, for example, superposition state of the photon, left plus right, which means horizontal polarization, onto the atom, which is in the superposition of G and E. So they're two separated. Now they bounce, dup, dup, nothing more. No? I mean, they come together, they bounce and fly apart, and that produces this state with a minus sign here due to this reflection mechanism, this pi phase shift. Only if the photon polarization is right and the atom is in E, there's a phase shift. And this can be rewritten in this state, Hg plus Ve. So we are producing from a product state, initially, we are producing an entangled state. And this is this identifies a gate. The quantum gate can be used to entangle two systems, and this is the entangled state that comes out. So here are the experimental results. We take this H photon, send it on this atom, and make that state very much as I said it before. And this is a density matrix, or more precisely, the magnitude of the density matrix of that particular state. And the fidelity with the expected Bell state is 80% in this case. And what can be done once can be done twice. So we have this atom cavity, so we take one photon, dup, dup. We take another one, dup. And then we make a GHZ state. very much according to the same lines. Two H-polarized photons, one after the other, bouncing from a system which is the superposition state, and makes this GA set state. And this is again the density matrix, or the magnitude of that, which shows the fidelity with the expected GA set state. This is the expected state, this with 61%. And in principle, that can be scaled up, and we can make larger entangled states. But we can do more. We can build a memory. I'm coming back to this memory issue. Please remember, when we just send a photon into our system, we store the photon. Of course, we don't know. Was there a photon? Was it stored? We don't know. We hope there was a photon coming in, but maybe there was no photon. So we need a Herald. We would like to know whether the other node, which is maybe 1,000 kilometers away, sending a photon through an optical fiber, whether this photon actually comes or not. We don't know. We hope that it comes, but hope is not sufficient. We need to measure it. And this system can measure it. So let's assume there's a qubit, a photonic qubit coming in the superposition of H and V with coefficients alpha and beta. So these are the unknown coefficients which are in the photon, and which I would like to store in the memory, which is my atomic state G plus E. So this is the light, and now I'm bouncing these two. So what happens is that the photon comes back in H or V, and the atomic state very much according to the mathematics that I've shown you before. The atom in the superposition of G and E with coefficients alpha and beta, or in the superposition of E and G with coefficients alpha and beta. So now there are two scenarios, two possibilities. Either I have this state if the photon is H, or I have this state if the photon is V. So let's make a measurement on the photon. The photon is still there, make a measurement on it. And if the measurement is H, or the measurement result gives H, we keep that state. If it's in V, then we just flip E and G. And then we know that, so to say, the state of the atom is alpha G plus beta E. Okay? So we measure the polarization, we do feedback on the atom, in case we need to do feedback, in case we measure the V, and then we have that state on the material object. So there's a Herald. I know that there was a photon, it bounced it off the system, and the state of the photon now lives on the material system. And it's just big, it's just a reflection mechanism, plus feedback in this case. So here's basically the scheme. The photon comes, it's reflected, it goes back, there's a polarization measurement, and now depending on the result of the polarization measurement, I do feedback or not. And this gives us a memory which has an efficiency, write-read efficiency. This is remarkable, of 39%. So remember, the other experiment I showed you had 20%. This is almost twice the efficiency, the combined reading and writing, with a fidelity of 86%. So this works wonderful. Now let's sort of say scale this up and see whether we can make not only gates between atom and photon, but whether we can make gates between two photons with basically the same mechanism, the same reflection mechanism. So here would be the protocol. You take the atom, bring it into a superposition, and bounce a photon and make a gate. This is basically the gate that I've shown you before. We take the next photon and make another gate, like this one here. Is that now a photon-photon gate? Because we are just bouncing off the system two photons? The answer is no. It's not a photon-photon gate because the second photon, namely this one here, sees the influence the first photon had on the system, because we made a gate here. Okay, so the first photon can influence the second one. But of course in a gate you want a unitary evolution, a unitary interaction, so it should go both ways. So basically what you need to reflect the first photon again and make another gate. We choose to use a slightly different protocol. We make a measurement here. We make a measurement on the atom and make feedback, very much like what we did in the quantum memory experiment, where we do feedback on the atom. Here we make feedback basically on photon number 1. And it can be shown that this is very much the same, the same as before. So here's the experiment. We have this atom with all kinds of preparation beams, laser cooling, and so on. And two photons are coming in, like this one. In this case, we're using attenuated laser pulses. They're basically attenuated here in this non-polarizing beam splitter. The two pulses represent qubits that bouncing off the cavity, and we send one in a delay fiber for the second photon to bounce off, and making fluorescence measurement on the atom, which produces a lot of light. Set this on a single photon detector, and having some fast feedback algorithm on the first photon here. And then the first photon comes out after this feedback, and then the second photon just goes through. And this is, for example, a C0 experiment. It's a classical probability distribution. I don't want to go into details here, but we can make an entangled state. For example, with this protocol, we can take two diagonally polarized photons, entangle them in a kind of DL plus AR state, with a fidelity in this case of 72%. So this is a density matrix, or again, the real part of the density matrix of this photon-photon gate. So this works all very fine. Let me just sort of say in 1 minute or 2 minutes because we tried. Okay, so many people come out and say to me, well, Gerhard, cavity QED is so difficult. No, it's not difficult, in my view. But many people say it's difficult. So let's get rid of the cavity. But of course, then with one atom, you can't do anything, because this photon doesn't interact with one atom. So we take an ensemble, a large ensemble. But the large ensemble is not so non-linear. We need a non-linearity. The non-linearity we're now employing is a Rydberg blockade mechanism, as was beautifully proposed by Amisha some many years ago. So basically what we now do is we take our photon, which is in a right and left circular depolarization, and store the right polarized state in the ground states of the atom. These are two ground states here, and takes the left polarization state and bring it into a Rydberg state. Store it in a Rydberg state. EIT, ramp down the light field, so store it. Store this one photon, give it the left polarized in a Rydberg state. Now the second photon comes, the target qubit, basically. And the target qubit is again in such a way that if it's right polarized, it doesn't interact. But if it's left polarized, there's a dipole-dipole interaction between Rydberg states addressed by the control qubit in that polarization and the target qubit. And the density and the state and the blockade radius and so on are tuned in such a way that in this particular case, the left circularly polarized photon gets a phase shift of pi. Only in this case. This is a complicated experiment. I tried to summarize 2 years of work or so in 2 minutes. But this is the essence, so to say, of how it works. And this is one of the experimental results that we achieved, where we can again entangle two photons, let's say two H polarized photons, go into a LH minus IRV state. And this is a density matrix, the real part and the imaginary part of that density matrix, which shows that yes, actually a Bell state can be made. The fidelity is not as high as in the cavity QED scenario, but it's significantly above the classical threshold of 50%. So 63 or so percent fidelity that we can actually achieve. So yes, one can do photon gates without cavities, but one needs a big nonlinearity, and this big nonlinearity is this Rydberg blockade in that case. And it works beautifully. Maybe not as simple as cavity QED for someone who knows how to implement a cavity QED system, like me. Let's make an atom-atom gate, but very quickly. So I take two atoms in a cavity, and they're both, so to say, let's say they're both in the ground state and not coupled to the cavity, because the cavity coupling comes here. So if I bounce a photon, I again get a pi phase shift. You remember? Pi phase shift, because it goes in and comes back out. But if one of the atoms is in the excited state, let's say this one, it doesn't go in, there's zero phase shift. It doesn't go in, zero phase shift. It doesn't go in, zero phase shift. So this is exactly, so to say, what you need for a quantum gate. If you rewrite this scenario in a Bell state basis, and these are the four possible Bell states, you would see it's a C0 gate. This is what I just described. It's a controlled NOT gate where the state The EE minus GG goes into EE plus GG, and the corresponding EE plus, this one goes into this one. So this is a controlled NOT gate. So we would like to do this experiment on that band states to demonstrate that it's a C0. The other gates that we've shown are phase gates, but this would be a C0 gate. So how do we prepare band state in a cavity? How do we do this? Well, carving. Carving is a technique. Let's say we take two atoms independently in a superposition. The perfect band state is the EE contribution would be missing and the GG contribution would be missing. So if we just have this one. Okay? So let's get rid of EE and let's get rid of GG. This is what's called cavity carving. So this needs to be eliminated and that needs to be eliminated. And we're left with this one. How does cavity carving work? Here's an example. So we take the EE contribution, or if the EE contribution exists, we reflect a photon. Again, it's this reflection process, but let's say now it's an anti-diagonal polarized photon, which is this superposition. We send it onto the system, it comes back, reflection. And it rotates the polarization from A to D, exactly due to this pi phase shift. The pi phase shift occurring when the photon is in R polarization. So the A changes into D. Okay? So here's a total scheme now. The EE with the A photon turns into a D photon, but of course the atoms do not change. The A changes to D. It doesn't matter whether I have two or one. One of the atoms in excited state. So EG goes rotation. Rotation, 90-degree rotation. Only if the system is in DG. A polarized photon stays an A polarized photon. So only in this case nothing happens. Here something happens. So if I reflect the photon, it stops now. It's okay. My feeling is it stops. So only in this case A stays A. But here the A changes into D. So I'm taking my photon, I'm bouncing it off, and I'm looking for polarization rotation. And if the polarization rotates, then I have realized one of these, and I can eliminate this one. It's my Herald. And I'm doing it twice, in the sense that now I'm transferring the EE into GG, and the EG into GE, just making a pi pulse. And then I can do it twice, and then eliminate also the upper one. And in this way I can produce band states. In this case with 80% probability. So we haven't optimized it totally, but we can produce these band states in such a way. And these are now the input to our gate. The input to this atom-atom gate. And this is the atom-atom gate in a total quantum circuit diagram here. I don't want to go into details. But the gate is just taking one photon and reflecting it. Again, it's just photon reflection. It's a very simple mechanism. It's not even a qubit, it's a classical photon, if you like. A classical photon, what I mean is it has a certain polarization, and it's not a superposition of polarizations. And this is the gate output. So please remember, I'm preparing the states here, with something like 80% probability. And then this is the gate output, 80, 80. So it flips here, it's a controlled NOT, as I said. So it goes down a little bit. It goes down. So the fidelity in this case is 74%. So we're going from 80% to 74% or something, which means that the gate itself has a, I don't know, 90% or so fidelity. It's not as easy as this one, but very rough estimate. Okay. So maybe as a final example, I don't know, my time is, I think, over right now. I have 5 minutes. You want to give me 5 minutes?
Sure.
Because I would like to show you something which is kind of interesting and neat. And this is basically now going from discrete variables to continuous variables. So everything I told you was in terms of photons and light and left polarization. The photon is nice because it can propagate, and once you detect it, you know it's there. So the photon in some sense is its own herald. But of course the efficiency is small. So the efficiency of photon production is maybe small, the efficiency of propagation is small.
the efficiency of detection is small. There are always efficiency issues. So why not make a big light pulse? That would be nice, isn't it? Just make a big light pulse. Many photons in it. And I mean, the big light pulse can, okay, it can be attenuated, but it's still there. It doesn't disappear as a single photon. So why not go from droplets, if you like, droplets to some more extent. So now I'm not talking about qubits, which depends, let's say, 0 plus 1 or right and left polarization, but now I'm trying to talk about qubits, which are kind of living in phase space, if you like. So I have a coherent state, an intense coherent state, alpha, and maybe a coherent state minus alpha, and some superposition state, alpha plus minus alpha, or alpha minus minus alpha, on the equator. And of course, all the other states. This is a kind of strange scenario because alpha plus minus alpha is totally orthogonal to alpha minus minus alpha. So this state here is orthogonal to that state, but this state up here is not orthogonal to that state down there. Alpha and minus alpha are not necessarily orthogonal. If alpha is large, and they're widely separated in phase space, and then it's okay. But if it's kind of small, let's say of the order of 1 or so, the overlap is finite. For example, for something like 1 photon on average, or coherent state amplitude around 1, well, I have an overlap squared here, which is maybe less than 1. Sorry, less than 1%. So it's kind of okay, but still there's a conceptual difference between what I said before with unitary evolutions on the Bloch sphere, with this thing which cannot be realized in a unitary way because of the orthogonality. So the question is, if I have a state alpha, how do I rotate the state to that one? It is non-unitary. So I have to do more. For example, I have to do measurement. The measurement is non-unitary. Okay? And the idea is like the following. So we again take photon reflection, or now it's not photon, but now it's light pulse reflection. So I'm still having my cavity QED scenario. I have the element E, and I'm bouncing an intense light pulse now, alpha. And it gets no phase shift because it cannot go in, so alpha stays alpha. But if it's in the other state here, the atom is in the other state, alpha goes into minus alpha, as I said before. Okay? So now if the atom is in a superposition, E plus G, and I'm taking my light field, and I reflect it, I end up with an entangled state. E times alpha plus G times minus alpha. Okay, it's an entangled state. So even if I take an intense light pulse, bouncing it off, it's an entangled state. It's actually a Schrödinger cat state. Depending on the size of alpha, it's a cat, or maybe it's a kitten. In our case, it's more like a kitten. But it's different from Schrödinger's cat experiment because this cat doesn't live in a box. This cat lives in free space. It's a propagating light pulse. Or a fiber or whatever. It's a huge cat because our pulses are typically kilometer long. Okay? So it's basically a cat state which is distributed over something like a kilometer. Again, this goes back to proposals of Duan and Co. So now what I do is I make an, I told you that I want to prepare this coherent superposition alpha plus minus alpha. So what I do, I take the atom and use the fact that they are in a entangled state. So I rotate the atom, let's say by 90 degrees. And if I do this, I end up with a coherent superposition of the atom in E or G and the light state in an odd, so-called odd state or an even cat state. The minus here state is odd cat because it only contains odd photon numbers, and the even cat is called even cat because it contains only the even photon numbers. Okay? So the odd cat is odd photon numbers, the even is even photon numbers. And here's the weakness function of such an optical cat as we measured it in the experiment. So it shows two blobs, which are the coherent blobs. This is the size of this cat is 2 photons. So we're bouncing a light pulse. story. The light pulse that comes back has a coherent state amplitude of 1.4, which corresponds to 2 photons. So there's a coherent state like this one here, there's a coherent state there, and there's a significant negativity in the Wigner function, which basically means it's a quantum state. Negative. The negativity in this case is quantified as something like close to 12% or so. But it's negative, and negative means it's really a quantum state in this Wigner function. So we do see negativities, and we do produce coherent state superpositions in this case. In this case, the odd case, by making a measurement of the atom, so it's post-selected, 50% success probability. So we're making this odd case state. The even here distribution. If you look from top, this is actually the even cat state here. It looks like this, or like this. And this is the odd cat state. So what is the difference between the upper and the lower? Well, this is what we detect in our detector. It's actually measurement. But there are losses. There are losses between the cavity reflection and the detectors. There are optical isolators, for example, in the experiments that we need, and they make losses. But we can sort of say calculate the losses or the effect of these losses on the cat state, and we can calculate what the emitted state looks like. This is what the emitted state looks like, and this is what we actually detect. So there's this negativity here for the odd cat state. The even cat state doesn't have a negativity. But the odd cat state has a negativity. So this is 11% or so. Actually, the even cats, well, maybe I jump over this because I'm running out of time. So the even cats actually squeeze. So we're producing squeeze light in this way. And the amount of squeezing is something like 1 or slightly more than 1. Well, this atom rotation is maybe more interesting because we have this entangled state between the atom and the qubit and the phase, the coherent state superposition of the light field. And because of the entanglement, we can rotate the atom into a certain direction, make a measurement, and then, due to the entanglement, produce different cats. So in some sense, we can tune the cattiness, if you like. So this is, for example, the input state. This is the output state after the pi reflection, or we can make these two states that I showed before, or something in between. So we can tune the cattiness, or we can tune between even and odd cavities by just making rotations on the atom and making suitable measurements. So it was a little bit fast, but my time is over. So let me jump to some conclusion slides. So the question is what to do in terms of the internet, quantum internet. And my view at the moment is a kind of moving thing. My view at the moment is probably when we go to long distances, we will use photons, probabilistically generated photons, which are then non-demolition detected, heralded while they propagate. But maybe on short distances, we can use these cat states, because this cat state is really a deterministic protocol. The beauty of the experiment that I showed you before, in every trial, in reflective photon pulse, in every trial, every attempt, we produce a cat state. It's completely deterministic. There's a probabilistic aspect because we don't know whether we produce one cat state or the orthogonal cat state, but it is a cat state in every attempt, which is kind of nice. But these cat states are very sensitive to losses when they propagate. There are proposals for error correction schemes, but I'm not sure how easy they are to implement, in particular at the low photon numbers that we have. Anyway, I can think about some short distances being using deterministic fields and long propagation, long distances using more of this photonic aspect. And this might also explain, and this is a little bit the kind of speculation that I wrote last night in the plane. kind of speculation. The question that's somehow driving me: why are quantum systems that we see in the world, why are they so small? typically they are small. That's where quantum physics comes from. I mean, if you look at correlation lengths or so in solid state systems or so, they are typically quite small. And my answer to this is really some speculation. We can talk about this. My speculation is when we describe these correlations, or when we describe this, we're describing in terms of fields. And fields are very sensitive to losses. And so maybe this description that we have on strongly correlated many-body systems, for example, based on fields or using very often these fields, have some truth in it because they cannot really propagate a long distance. Photons can propagate a long distance, but they get lost, and also that's why we need this heralded schemes. And basically, this is, to my view, the reason why we don't see gigantic quantum systems in the world. Anyway, this was my last slide. This is my last slide. Shows the group. There's a team of students, a wonderful team of students, and we were recently in this castle. This castle, which you can see after you've seen the group. We've contributed to the experiments. I mentioned some of the names after this, and this also gives some reference to tonight's Halloween. So, thank you very much.
Time for a few questions.
So if you want to do this some communication with the cat state, what is the advantage in the cat state, and what is the number of photons in the cat?
I actually skipped one slide which shows how it should be used. Maybe I can show this. We look here in this one. The cat state shows these interference fringes between the coherent bonds. And we can plot the visibility of these fringes, defined in a suitable way. We can plot the fringe visibility as a function of photon-number. And then we see this is for the detected cats, and this is when we take into account the losses and calculate how the emitted cats look like. So this is alpha squared is photon-number. So we were typically working in this regime, 1 or 2 photons. But you can see when we look only for the emitted cats, we could go to photon-number 4, 5, 6 or so. This is the cat size roughly that we have at the moment. But they are made in every attempt. This is the advantage. If you try to emit a photon, push a button, the probability that no photon comes is about 40% in our experiment, which is already quite large. And in this case, it's 100%. I think this is a wonderful, it's a wonderful system. And also the homodyne or heterodyne system that we use to detect this has 100% efficiency. The detectors that we're using have 50% detection efficiency. So in some sense, I would think if I want to build something deterministic, and this is what we would like to do, and maybe this is what nature wants to do, it's better to communicate with fields. Maybe quantum fields, cat states. Does it answer your question somehow?
Some question about Harry.
So with an atom entangled with, say, a single photon, when one looks at correlations, often it's kind of post-selecting on getting a clip from the single photon. So that in a way it's kind of working in the subspace where the photon was not lost along the way. Is there an analogous notion with cat states with several photons, let's say?
Well, one probably has to distinguish or make some measurement which tells me that the cat state is still a cat state. So let's say the beta function is still negative. We're thinking about it, but there's no established. I don't think there's an established way of how to do this. But let me go one step further. So So you were asking for the post-selection, basically. So all the data I've shown you with the photons are, of course, post-selected. Unfortunately. The coherent states, the cat states, were no post-selection whatsoever. Just what we detect. And what we detect is this. Detected and emitted. Well, emitted is not detected, but detected is detected. Yeah, there's no standard protocol. No, there's no standard. Yeah, okay, there's no standard protocol. So I can't answer your question. No.
All right. So let me just ask a short question. So what's quantum internet? Is it a vision or fiction? Maybe.
But the point is, this is a toolbox. I think this is the toolbox that you need.
So it's a vision.
It's a vision. And in the end, I'm very optimistic. I'm very optimistic. But of course, there's work to be done.
On this positive note, let's thank you.